Hello students, today we are going to study about the cryptography and its mathematical approaches. What basically a cryptography means. In today's world, security has become a major concern and the entire world is 80% to 90% dependent on the data transfer. And data security is the vital scenario where we have to work. Right, so cryptography basically means to encrypt a message that is being sent by a sender and decrypt at the receiver end. So the entire process is known as the cryptographic system, okay, or cryptanalysis process. So in through cryptography we can easily securely send our message without having a worry about if anyone can hack our message or hacker can easily read our message. Next, in this video, we are going to study about its mathematical approaches, right? How we are going to choose our public key and private key and how we are working accordingly, right? So what do you mean by prime factorization? Prime numbers are the basic constant when determining a public key and private key, and many various algorithms uses a prime number to design a very difficult and complex key. Okay, so prime factorization basically means to factor a number n is to write its product of the other numbers, right? Factorization is relatively hard as compared to multiplying the factors together. Prime factorization is basically when we factorize a particular number into a prime numbers or multiplication of products of two prime numbers, right? For example, 91 can be have a prime factorization of 7 into 13. Okay, another number that is 3600 has a prime factorization of 2 to the power 4 into 3 square into 5 square, right? Likewise, we can have any prime factorization, but it is hard to calculate. Next term or terminology that we should know is the relatively prime number. So what do you mean by relatively prime number? Two numbers, that is 8 and 15, are relatively prime if we get a common factor between these two numbers as 1. So if I say two numbers are relatively prime, then the common factor between those two numbers should be 1. Okay, so here we have taken the example of 8 and 15. When we factorize 8, we get 1 2 4 8, and 15 we get 1 3 5 15. So 1 is the only common factor between 8 and 15. So 8 and 15 are known as relatively prime number. Okay, the next term here I have discussed, that is the greatest common divisor. Okay, so by comparing the prime factorization and using its least power, we can determine the greatest common divisor. As you can see in the example, that is we have taken 300. We have prime factorized 300, that is 2 to the power 1 into 3 to the power 1 into 5 to the power 2, right? And another number 18, that is 2 to the power 1 into 3 square. Okay, now when determining the greatest common divisor, we will take the minimal power of the prime factors number. Okay, and we got what? 6 is the greatest common divisor for the number 318. So this is how we will calculate the greatest common number. So what is the use of GDC? Why I have told you the relative prime number concept and prime factorization concept? Because we are going to study a Euler torsion function, also known as the phi function. It is denoted by phi. What it says basically? It says if we take any number that is greater than or equals to 1, means number is positive, and it is defined as the number of positive, what is function returns, it will return the number of positive integers that are less than n and which are co-prime to n. Okay, so let me clear this. What is co-prime? The number where GDC is 1. Okay, if we have two numbers, then and if their GDC is 1, then those two numbers are known as co-prime. Okay, suppose we have taken an example of 5. So 5, if we calculate the torsion function for 5, first of all what we have to do, here n is 5, then obviously it is a positive number, so no issue. Next we have to find out the number less than 5, that is 1 2 3 4. Okay, now we will calculate the GDC between 1 and 5, 2 and 5, 3 and 5 and 4 and 5, right? And we can see that with 5 here all the number have the GDC 1. Okay, so the count, the Toshan function says I will tell you the count, not the number, not the numbers which are present in the set. It will tell the count of the numbers present in the set. So 5 of 5 is 4. Okay, now next comes, we have taken another example, that is a 5 of 6. Now what we will calculate the GDC of the numbers less than 6 with 6, that is 1 to 6, 2 to 6, 3 to 6, 4 to 6 and 5 to 6. Here we get only two numbers that have the GDC of 1. Okay, and it will give a count of 2. So this is the case of totient functions. But what is the benefit with a prime number? Okay, if n is a prime number, in the last slide we have discussed with any number, not a prime number particularly. Okay, but if n is a prime number, then we have a totally different story, that is we don't have to find the GDC of each number that is less than that particular n. We have a direct formula, that is phi n is equals to n minus 1. So this is a beneficial with a different kind of benefit we are getting with the prime numbers, that is we have a predefined formula, that is phi n is equals to n minus 1. So phi 23 is equals to 23 minus 1, that is 22. Directly we can say that any prime number, or if n is a prime number, then the totient function return n minus 1. Okay, see, we have four rules, that is phi of 1 is equals to 0. Of course the one don't have GDC with anything else, because less than 1 is 0 and we can't move there, right? Phi of p is equals to p minus 1, where if p is prime. Okay, phi of m into n, if we can break any large number into two numbers, then we can, and such that these two numbers are relatively prime, means if we factorize this number, not prime factorize, general factorize this number, and we get a common number, the common factor as 1, then they are relatively prime, right? So in that case we can write directly that phi m into phi n. Okay, and if we move towards the power, okay, phi p to the power e is equals to p to the power e minus p to the power e minus 1 if p is a prime number. So these are the four formulas we should know. Now we will move towards the numerical part. Okay, let's try some examples, that is if you want to calculate the phi of 13, as 13 is a prime number, we can directly do that, that is phi of n is equals to n minus 1, that is 12. Okay, what is the value of phi 10? As we can say that see that the 10 is not a prime number, so we can't directly denote it, or the other traditional way is to calculate the GDC from 1 to 9 with 10. Okay, rather than we move to the other part, that is we will divide the 10 into two numbers that are relatively prime with each other. So we have 2 and 5, and coincidentally 2 and 5 itself is a prime number. So we get what? Phi of 2 is equals to n minus 1, that is 1, and phi of 5 is equals to n minus 1 is equal, that is 4. So we get 4. Okay, okay, what is the value of phi 240? We can first of all prime factorize this number. Once we prime factorize this number, we get 2 to the power 4 into 3 to the power 1 into 5 to the power 1. Now here the fourth formula, that is p to the power e, comes into the existence, where phi of 240 represent 2 to the power 4 is p to the power e minus p to the power e minus 1, right? So we will apply the same formula to each and every prime number, and we get what? 64. Similarly, the last but not the least example, that is phi of 49. We can directly say that phi of 49 is equals to phi of 7 into phi of 7, but 7 and 7 are not relatively prime with each other. So this solution is wrong. We have to say phi of 49 as 7 square, which comes to the fourth formula, that is 7 square minus 7 to the power 1, that is 42. So here comes the end of the Euler's torsion function. Now comes the Euler's theorem. What the Euler's theorem state? Euler's theorem basically uses the Euler's torsion function. What it states that if we have two numbers, it states the relationship between two numbers. If we have two numbers, that is x and n, such that they are co-prime, means GDC is 1, and then we can write that number into this particular formula, that is x to the power phi n is equals to 1 mod n. Okay, x is equals to, I have taken an example where x is equals to 4 and n is equals to 165, and we have calculated the GDC and it comes to be 1, so they are co-prime with each other. Okay, now as the formula state, we have to calculate phi n, so we will divide that 165 into two numbers, that is 515 into 511, because 515 and 11 are relatively prime with each other, but 15 is not a prime number, so we will again divide it into 53 into 55. Now we can easily apply the formula of prime numbers, that is 2 into 4 into 10. Okay, what we get? 80. Now we will put the value back into the formula, that x to the power phi n is equals to 1 mod n. So 4 to the power 80 is equals to 1 mod 65. Why we are doing in the entire process, why we are doing this? Because as you can see that 4 to the power 80 is a big and complex number. This number we can easily use to form the public key or private key, which is not easily decodable, right? And whenever we will divide 165 with 4 to the power 80, then we will get a remainder of 1. So it is the easiest way to calculate and decode the primary and public key. Okay, next comes the Fermat theorems. Fermat theorem is a special case of Euler's theorem. What it says here, it has added two more conditions, that is, if we have two numbers, the n should be prime and x should not be divisible by n. Okay, I repeat, n should be prime and x should not be divisible by n. Okay, so if these two conditions follow, then we have a formula x to the power n minus 1 is equals to 1 mod n. Okay, this is known as the special case of Euler's theorem, because as you can see that what Euler's theorem says, x to the power phi n is equals to 1 mod n, right? This Euler's theorem says, and if we know that n is a prime number, so we can write that phi n is equals to n minus 1, and it will generate a Fermat's theorem, right? Example, x is equals to 3 and n is equals to 5. Okay, then we will put the entire formula, we get 81 is equals to 1 mod 5. Whenever the 5 is being divided by 81, we will get a remainder of 1, right? There is another a small variation of Fermat's theorem, that is, if we multiply x to the Euler's theorem, we will get another brand new formula, that is x to the power n is equals to x mod n, where the GDC of both the numbers x and n should be 1. So this is how we have used different theorems and algorithms to calculate public and private key, and these algorithms are very useful in the case of cryptography. Hope you people got the point what I was trying to told you. Thank you.